this tutorial we're going to have a look at probability distributions. Now they all happen in Autograph in the stats page and in the advanced level. Here you have a single variable along here, and up here goes frequency, or as we're going to do it, probability. So right click, enter probability distribution. These are the distributions we have to choose from. We have rectangular, discrete or continuous, binomial, Poisson, geometric are discrete, and you can add your own user-defined discrete distribution, the normal distribution, and you can define any function of x. Let's have a look at binomial. And here your two parameters are n, the number of attempts at whatever it is that you can succeed or fail in, and this is the probability of succeeding. So let's have a look at, for example, 50 17-year-olds taking the driver's test in the UK. Now the probability of passing at the driver's test is 0.47 for 17-year-olds. If we press OK, we're going to get a distribution. What's the mean? Around about 25. What's the standard deviation, and so on. So have a think about the shape before it reveals itself to you. And there's the mean. What we can do is right click, show the mean in 3 standard deviations. So there's the mean, 1, 2, 3, 1, 2, 3. As soon as you put another object on, of course, that becomes the current one, and the right click options are not too numerous for that object. If you go back to the binomial, you can, for example, fit a dependent normal. Well, you would expect it to be fairly normal because the mean is, if we go back to the binomial distribution and double click on this, the mean is 23.5, standard deviation of that. The point being that the probability is nearly a half. And so it's a very well balanced distribution, and the normal distribution will fit it very well. This is quite nice. This is the animate object, so we can change n, and whatever you do to n, it'll still be a good fit because we're not changing p, so the normal distribution will continue to fit it like a glove. On the other hand, if you change p, and not a lot of point in changing p with a step of 1, but we could change that to a step of 0.1 and see what we've got. It's probably better if we set this to something like 0.5 first rather than 0.47. Let's do that, 0.5, then it's going to go all the way down to 0. And at the other end it's going to go up to 1 at 50. That is everybody passing. If you again select this, you can do probability calculations on this. You can say what's the probability of at least 30 passing, and there it goes. It's a discrete distribution. You can drag this about, but it's nice to see that this does in fact have a finish. It finishes at 50, and that's fine. So binomial distribution, lots of possibilities. The other one that's of course very popular is the normal distribution. So let's have a look at that. Enter probability distribution, normal, OK. Let's have a mean of 100, and let's have a standard deviation of 15. Now that's the model that's used for IQ tests, so that's not a bad one to look at. And right click, mean of 3 standard deviations. So 1, 2, 3, 1, 2, 3. You're never going to get much more than 3 standard deviations either way. We could select that and right click, do some calculations on this, and this is where you also get the opportunities to do inverse calculations. So for example, find x for which the probability that x is bigger than a certain value is 10%. So we're looking at the top 10% of this, which should be about there, one-tailed. If we did two-tailed, it'd be 5% at either end. So let's have a look at that. That's pretty good. Now what you could, if you're teaching this at a higher level, you might say that this is h0, and then h1 will be another normal distribution, so let's put that in. So let's supposing our alternative hypothesis is that we've got a super bright lot of people here, and so we're going to enter a probability distribution of normal of, say, a mean of 120 and a standard deviation. Let's keep that the same. So that's going to produce another distribution over here, and we're going to call that h1. Now, a type 1 error is saying that although we're thinking of rejecting h0 under these circumstances and accepting h1 because the numbers is too high, in 10% of occasions this will be perfectly right, because in 10% of h0 they're going to be there anyway. So that's rejecting falsely h0. Accepting falsely h1 is the alternative to this, which is a type 2 error. And let's have a look at that. So we want this particular value here, so I'm just going to select this and see the value is 119.2. So we now go to the second normal distribution, h1, and to see how likely it is to have a probability, a value of greater than 119.2. Let's put that in, 119.2. But actually what I should have done is less than. Now that's for type 2 error, that is accepting h1 when you really should not be, and this is rejecting h0 when you really should not be. You can also have a look at this in raw data terms, because you can use any of these distributions to create some data. So I'm going to select a normal distribution and I'm going to edit it. I'm going to do the one we've just done, which is 100 tab 15, and let's have 1,000 of those. Ready, steady, go. So we have 1,000 items of data. And what we could do is sort it by X and just see if we can be sure that everybody's understood what's going on here. If we sort by X, well, it's a mean of 100 and standard deviation of 15. We will not expect much below 315, which is a 45. So 55 should be about the minimum here, maybe 1 or 2 under. Let's have a look. Okay, we've got 1 under 55. At the other end, 145, let's have a look. 2 over. So in 1,000, that's really not bad. The next thing you might consider is that IQ tests are all whole numbers. So what we need to do is use the scaling option here to make these all integers. So I'm going to put int brackets x. Now that's all very well, but what the integer does is truncate. So that 53.5 is actually going to end up as 53. We really want it to be ended up as 54 because it's more than halfway. So I'm going to add a half to each one, plus 0.5, and then scale it, and that should make that one 54, and this one should be 55. Are you ready? Steady, go. 54, 55, perfect. It's done the job nicely. Right click OK, and that's raw data, but we could have done that. Double click, we could right click, edit the column header, and let's call it IQ scores or something like that. IQ scores, and use that as the dataset name and the x-axis label. Perfect, there it goes. Okay, what have we got here? We've got a dot plot, possibly. That's the data we've just discovered. We could fit that into a histogram, but we can't do that until we've grouped the data. So let's group the data. It's offering us 0 to 200 in classes of 20. Yep, I'll buy that. Let's just see what we've actually got. Those are the classes and these are the frequencies. That's good. We know it's discrete for sure because it's whole numbers. So that's good. Right click, histogram, frequency or frequency density. We'll talk about that in a minute. Often shoots off the top because these are different concepts really. This is a grouped frequency and this is individual raw frequencies. Likewise, what we could do is see how well an actual normal distribution fits it. So I'm going to go normal. This time I'm going to fit to data. So I'm going to take the value of the mean of the data and the standard deviation. Look, we did a pretty good job there with our data. Mean of 100 and standard deviation of 15. Fantastic. That extra half just made the difference. Fit to data. Okay, now what's going to happen here? You've got to remember that these are completely different animals. We've got a frequency distribution here, straight frequency, and the total area here, goodness knows what it is because we haven't even thought about frequency density, and a normal distribution, which is a distribution with a total area of 1, so it's going to be absolutely tiny down the bottom. So what we could do is double click on this and think about frequency density for a moment. Now what does frequency density actually mean? It means that, for example, if you have a unit of 20, then nothing's going to change. That'll be 1 unit, so this will be the frequency, so this will indeed represent the area, that will be the frequency. So let's check that. Nothing's changed. If we move it to 10, then what's going to happen now is that that's going to be half an interval, So in fact this would be 2 units along here, and so this is going to have to be halved, so it's going to come down by a factor of 2. That's looking good. So if we take this all the way and do it down to a unit of 1, that way the total area represents the frequency. So we can now auto-scale, and we can see that things are beginning to look a bit better. This is our dot plot, which is not really relevant, so we'll get rid of that. But the histogram has a total area of n, and what we've done with the normal distribution is that we have actually scaled it up by, if we just check on normal distribution, it says scaled by n. So the normal distribution usually has a total area of 1. It's been scaled up to have a total area of n, so that it does at least match the histogram. Another topic in stats that's quite useful is the central limit theorem, and for that we need to be able to take random samples from a good sized population. So I'm going to open up the data set that we get off TSM website, and weights of patients is great because we've got 7,500 weights of people here, so it's a nice big data set. So I'm going to copy that and stick that into Autograph. So right click, enter raw data, right click, paste, in it goes, tick tick, and we're off and away. So let's group that straight away. What's 200? That'll do fine, and do a histogram. So that's our basic data from which we're doing samples, and it's quite a nice one, this, because you can actually talk about the weights of luggage and the weights of people that get onto aeroplanes. They weigh your luggage, but they don't weigh you. And the reason is really very straightforward if we have a look at the central limit theorem. So let's do this. Let's do sample means. So from this 7,500 people, I'm going to take a sample of, say, 5 people getting onto a small aeroplane. So here it is. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So each one of these samples has a mean. So we are building up a distribution of sample means. And the sample means themselves have a standard deviation, which is called the standard error. And it's 8.4 kilos, so it's quite a substantial distribution. Do 100 of those at a time, that's fine. On the other hand, if we clear those samples and put 480 people getting on a big jumbo jet, single sample, bang, there it goes. Now somewhere in the middle of that is the mean, and let's keep doing this. And what you'll notice from the mathematics, the standard deviation of the sample means is less than a kilogram. So if we do lots of samples, we'll find that it's whippet thin, and so the pilot of a big aeroplane can know perfectly well what the weight of the passengers is because the standard error is so small. So that's some of the things you can do with probability in